All right. So yesterday we spoke about Faraday's law. I mean, we are talking in general about Maxwell's equations, but we spent some time on Faraday's law. And how about if you also find another integral among those four in which a line integral over a closed loop of a vector is calculated? So let's say that this is the first law, second, third, and fourth. So let's vote which also has a line integral, which law also has line integral in it. So is it law number 1, referred as Gauss's law? No. Okay. How about second law? It's also referred as Gauss's law. It's not. All right. Third has. How about fourth? Yes. Fourth also has a line integral. This time it's a line integral of another vector quantity describing magnetic field. This is called magnetic field vector. The first two are so-called surface integrals. And this integral is referred to as flux. So here we have flux of electric field vector, and over there we have flux of magnetic field vector. And I don't want actually to discuss concept of flux. It is new concept. It's not like line integral to which we were already exposed. We calculated work using line integral. All right, Matt, yesterday we also determined that there is a different interaction than gravitational interaction. And actually, how about if despite we didn't have to write the quiz, why don't we answer the quiz? So let me bring up actually the quiz for a moment, the picture of the quiz. And can we recall what were the reasons that the interaction which we observed was not gravitational? Is there a volunteer to say it? Yes. Because, for example, this interaction was repulsive. We had a configuration in which the two rods repelled each other. Gravitational interaction is only attractive. All right, so this was one argument. How about another argument? Yes?
Oh, we know it's not gravity because gravity deals with mass.
Correct. We were able to affect interaction of the magnitude of the interaction without changing the mass. Gravitational interaction is dependent on mass of object. This interaction was not. Historically speaking, however, this was the first interaction we recognized. In ancient Greece, people already recognized that this type of interaction exists. They noticed that. And actually, when we discovered, as humanity, that Earth is round, and what causes that we stick to the ground, the first attempts were to explain it in terms of electrostatic interaction rather than gravity. Later on, this was determined that the two interactions are different, and I think even in the Middle Ages, we still were not aware of gravity. We were aware of that, though. Right. Gravitational interaction and electrostatic interaction and magnetic interaction depend on relative configurations of interacting objects, and also on attributes of those objects. Each particle in the universe has a set of attributes, and Mass is an attribute which affects gravitational interaction. Charge and spin affect electromagnetic interaction. Mass and electric charge are scalar quantities. Spin is vector quantities. Now, we never actually saw particles. The way we observe particles, we are able just to let them to fly through something and they leave traces. And from that we can fantasize how they look like. And probably each of us, including me, thinks about particles that it's a tiny sphere. Sometimes it is so tiny that its dimension is 0. For example, we don't definitely know what is the diameter of an electron of which you heard of. It's a pretty common particle in our vicinity. All right. So if we take a look at objects, well, they are made from atoms, which in turn are made of particles of which you probably heard. The most common particles which constitute the matter in our vicinity are protons, neutrons, and electrons. Protons and neutrons occur in nuclei of atoms, and electrons somehow orbit is not the right answer today, but we can say that, well, they appear in the vicinity. Bohr actually came with an idea that electrons orbit, but contemporary physics doesn't recognize that they really orbit. They form clouds of which are referred to orbitals. But you can think about it, that they orbit the nuclei. All right, so in order to see how the particles, these particles interact electrostatically with each other, we have to know this single attribute which is referred to as electric charge. And proton has a charge of 1.6 times 10 to minus 19 coulombs. Coulomb is an SI, or Standard International Unit of charge, and how big is 1 coulomb? We are not ready actually at this point to recognize how big is coulomb. 1 coulomb actually is a huge charge. On the other hand, proton has the smallest non-zero possible charge available in the universe. If objects change their charge, and we see how objects can change their charge, it happens by this amount. This is the smallest amount by which it is possible to change charge of an object. And charge of a proton is really tiny, very close to 0. However, it's not 0, and even that tiny value of this attribute can affect interaction quite significantly. Neutron is another particle which is actually necessary to build nuclei of atoms. Without existence of neutrons, protons cannot gather together to form more complicated nuclei. So if we had only protons, then we would have only hydrogen in our universe. Even helium, here we have actually a nucleus of helium, and the formation of nucleus of helium requires 2 protons and 2 neutrons. Without neutrons, the particle would not be formed, and the reason is that although charge of neutron is 0, which means that it does not interact electrostatically, there are 2 internuclear forces, strong and weak force, which balance all the forces in the nucleus and make the existence of nucleus possible. And to complete the atom, we will need electrons. Charge of an electron is opposite to charge of a proton. Letter E actually doesn't, it's a common misconception that E stands for electron. E stands for elementary. So that value, 1.6 times 10 to minus 19 coulombs, is referred as elementary charge. And proton has exactly the value of elementary charge. Electron has an opposite charge to proton. Well, if we look at an object, and and each object is a system of particles. We assemble particles and we get an object. Well, what we saw a moment ago, this helium atom is also an object. It contains 2 protons, 2 neutrons, and 2 electrons. So it's a system of particles. And charge of an object, by definition of charge, actually is the sum of charges of all components. So we will have to add charge of all particles constituting the object, and that way we would get the charge of an object. Now, we say that bodies are neutral when their charge is 0. When there is imbalance, so that we have more particles, if we add positive charge of all particles and negative charge of all particles, and we won't get a 0 number, we say that this object is charged. Now, depending on this, if we have more protons than electrons, then the object will be positively charged. If we have more electrons than protons in an object, then the object is going to be negatively charged. All right, how about as a puzzle, consult with each other what is the charge of an alpha particle, which is in reality nucleus of helium atom. So if we strip electrons from helium atom, we will get an alpha particle, and why don't we determine the charge of that particle? Consult with your neighbor. And actually, I'm more into, because obviously you probably can add it easily, I want you to now say it. Yes?
3.2 times 10 to the negative 19 coulombs.
It could be 3.2 times 10 to negative 19 coulombs. Now, you could also answer 2e, but I want to hear this in English. If I say 2e, the charge of a particle is 2e. And probably in your notes, it's until you get to the final answer, you prefer to think it that way, that it's 2e. Say 2e in English. No. 2 times the elementary charge, correct. Yeah, right. Now, if you want to change charge of an object, because yesterday in the experiment I was changing charge of objects by, let's say, rubbing rods against fur. What did I really do? How I was able to change the charge?
Transferring the charge from...
Transferring the charge. What do we mean now by transferring the charge? Actually, I tell you that in order to change charge, we have to do the same trick as if we wanted to change mass. So, for example, if we get excited into weight loss, which should be actually called mass loss, because if somebody is really, really fat on Earth and wants to get rid of, to get slimmer, going to the moon will reduce weight 6 times, but that person will be still fat on the moon. Yeah, so really we want to lose mass, not weight. How do we do? Compare changing mass with changing charge. What do we really do with the object in order to change those two attributes of the object? Consult with each other now. In fact, actually, let's follow this idea that we remove charge or add charge. How do we do that? Yeah, because I don't want you to think. It's also some kind of common error that we think about charge as some kind of fluid which we pour in and out of an object. What do we really do with the object? Do we what? I'm not asking how. What? Yeah, so let's say through friction, and I don't even know if it is through friction or what kind of interaction really is, but if we have two different substances, like a plastic rod and hair, something happens.
Are you transferring electrons?
Right. We are transferring objects. So actually, there is no other way to change charge of an object, but we have to change the object. It's the same way like we want to lose weight. We have to change object. We have to cut off something, for example, or remove it in some other way. We have to remove some particles, or we have to add some particles in order to change mass and in order to change charge. Ian is right that in our vicinity, actually the simplest way to change charge is by moving electrons. Electrons are relatively easy to move in and out. And, well, if I rubbed plastic against fur, I don't know to which one electrons had higher affinity to stick, but to one of those two substances, they prefer to stay on one of those substances. So they got from one, or let's say that we have such a rod that electrons prefer to stay on the fur. So when I rub those two together, electrons from the rod moved to the fur. Both objects were changed, right? Because now the rod didn't have those electrons which it had at the beginning, and the fur got extra electrons. So it created that imbalance and charged both objects. However, what can we say about charge of the rod in this situation? The total charge of the rod. It would be positive. There was deficiency of electrons, so there were more protons left. So the rod became charged positively. How about fur? Negatively charged, because now it gained electrons. So it became negatively charged. Now, if we take a look at the amount of charge which we transferred, well, we actually transferred zillions of electrons, however, their mass is so small that practically rod and fur didn't change mass. The change of mass was unnoticeable for us. It did change, but it was a tiny change. It's not like cutting out part of the rod and putting it on the fur. So when we transfer electron, we practically do not change mass of the object, but it is only practically. And however, the charge is changed. All right. Now, depending on this, what happens with charged particles, what can happen with charged particles in the substance, we classify substances into certain types depending on, well, something which is referred to as conductivity. And conductivity refers to this, what charged particles can do in the substance. So, if charged particles in a system cannot move, we say that the system is an insulating medium, or briefly, an insulator. And that plastic, for example, is an insulator. I was able to remove electrons from one side, and the electrons from the other side of the rod didn't go to that first one. They did not fill that emptiness left by the electrons. So in insulators, through insulators, charge cannot be transferred. Charged particles do not travel through an insulator. If charged particles can move almost freely, we say that substance of this medium is a conductor. And well, the most common conductors in our vicinity are metals. In metals, electrons can travel. And actually, because of that fact, we use metals very commonly in our households. Where?
Wires.
In the wires, right, to run electricity. In those wires, the electrons travel because they move almost freely in metals. But metals are not the only conductors. We can have electrolytes. So, for example, if you mix kitchen salt with water, you will also get a conductor. This medium will conduct. However, in that solution, it will be ions, which are almost freely moving charged particles, not electrons. There is a group of substances in which charged particles move with very significant restrictions. And here is a group. This is a group of silicon, germanium, gallium arsenide, indium antimonide, cadmium telluride. These substances are referred to as semiconductors. The restrictions very strongly depend on the external conditions. So, for example, if you change temperature of semiconductor, it can significantly affect its conductive properties. Even illumination. You can illuminate a semiconductor, and it will start to be like a conductor. In darkness, it will behave like an insulator. You can also create, well, we will learn about this, various fields in semiconductor and make it either conductive or insulating. Field electron transistor, for example, is based on this principle that we create electric field and create a channel through which electrons can travel. Yes?
Where would we find these semiconductors in our day-to-day?
On a beach. Yes. Yeah, actually, silicon is one of the most common elements on Earth. And it is on the beach, and I'm serious. We actually extract it from sand. Sand is silicon dioxide. Now, some of them are quite rare. Cadmium telluride is pretty expensive compared to silicon because these elements are not so readily available like silicon. And I'm not sure that this was the reason why silicon was used first. We say?
It's easier to work with than, gallium arsenide.
In what sense?
Being less toxic.
Oh, okay. I agree with that. Yeah, because technologies are simple for all of them. Actually, I mean, if you think about where we get materials, all of it comes from the Earth. Even those which we make artificially and those who exist for a fraction of a second, because now the elements which we have at the end of the periodic table now exist for a fraction of a second. All of it is taken from whatever we have around, which means from the Earth. All right, there's one more group of substances. They are called superconductors. And in superconductors, when a charged particle starts to move, it continues to move like it were free. Like there were no interaction. So charged particle will move with a constant velocity, or if it is bent with constant speed. Superconductors conduct electricity even better than conductors. This is why they are called superconductors. All right, now we are getting into something more serious, and we go now into the details of the description of interaction. And we will start from the interaction of an object with a particle. And rather than expressing it in terms of a force, we will divide, or we will introduce such a trick that we will describe it in such a way that the object produces a field, a force field, and when the particle is placed on that force field, it experiences the force. So what exerts the force? No. The object producing the field. Right. Now, this physical quantity, electric field vector, well, characterizes actually the object which interacts with the particle. It says how it is going to interact with particles. And I recommend that you practically memorize by heart the definition, which says that the electric field vector at a certain position, there is some problem with the print. At position R, this should be R over here, is a vector E of R such that the electric force exerted on a particle with charge Q placed at this position would be equal to the product of the electric field at the location of the particle and the charge of the particle. What is F? Can somebody say it in English? What's F? The force. Which force? The electrostatic force. Which electrostatic force? What do you mean of the object? Which object? Consult with each other, okay? And in the meantime, I'll fix this. Yeah, so have a talk and discuss with each other. All right. Yeah, so let's come back to this. What is F? Let's start all over. So it is force. Which force? Not of the electric field. We don't say it of the electric field. Let's say it's exerted by and on. All right? So let's say it this way. So what exerts the force? The what? Actually, well, we can say that the field exerts, although I prefer that you recognize that the field doesn't appear from nowhere. It's the source of the field, right? So it's the object producing the field. And so object producing the field exerts an electrostatic force. On what? On the particle. Okay. Which particle? The one which we consider. Where is the particle? At location R. Correct. All right. So this is an electrostatic force which an object producing the field exerts on a particle of interest located at point described by this position vector. What's Q? Don't tell me that it's charge. Yeah, because I know that. Charge, but of what?
Particle.
Which particle? The one which we are considering, the particle of interest, correct. So this is the charge of the particle of interest. All right. Now this is again complicated. What's E? Don't tell me electric field vector. Which one? Yes.
The source electric field.
The electric field produced by the source, right? So this is electric field produced by the object exerting the force. Okay.
Indicated with the L subscript L-ness or?
Electrostatic. Now, you confused me now for a moment, but I will be back on track. Which electric field vector produced by the object exerting the force? Which one? At the point of the particle, correct. At the point of the particle. All right. How about if we think about, well, so let's say that we have a certain source which produces electric field here. And so we have, let's say in this corner, we have an object which produces electric field at this point, it produces electric field at this point. Now if I take a particle and place in this location, I can find out the force. Which force? Exerted on the particle, exerted on this particle by the source. And in order to get that, I have to multiply charge of the particle by the electric field at this location due to the source. Now, if charge is positive, well, we have a product here. We multiply two quantities. Which product are we using here?
Vector product.
Vector product. Incorrect. A what? Number and a vector. Correct. Here we multiply a number and a vector. All right. So if the number is positive, and if we multiply a number and a vector, the result is going to be a vector. Correct. Now, if a number is positive, what can you say about the resultant vector? That it is in the same direction as the multiplied vector, as the first factor. So if the charge of a particle is positive, then the force exerted on the particle is in the same direction as the electric field at the location of the particle. Now this is not electric field of the particle. It will be common error. You will confuse what is the source and what is the subject of the force. All right, now if I place a negatively charged particle, then, well, we have to multiply a vector by a negative number. So what can we say about the directions? They will be opposite, correct. The SI unit of electric field, actually if we look at the definition, we can recognize what should be the unit of, in what units electric field should be measured, yeah, because force is measured in newtons, charge is measured in coulombs, so in order to have agreement, electric field vector should have a unit Newton per coulomb. And in this chapter, actually, in the chapter where we are now, indeed it is identified as the unit of electric field vector. Soon we will see that there is another unit which is equal to that and quite commonly used. No, that actually doesn't have a separate name. We don't have a name for the unit of electric field vector separately, like for force, for example, or for charge. We can, in the future, we will also be able to relate this unit, Newton per coulomb, to another commonly used unit, volt per meter. These are equivalent. Sometimes you can find Newton per coulomb, sometimes you can find out volt per meter. Now, in order to visualize, if we make a drawing, because electric field vector is a very good description of electric field algebraically. When we want to perform calculations, then it's convenient. But if we want to visualize a field, we can do it with a certain geometrical concept, the electric field lines. And electric field line is defined in such a way that it is a line along which the electric field vector is always tangent. Let's take a look at some examples of electric field lines. So, for example, if we have charged particles, electric field lines will be radial lines going away from the particle. For a negatively charged particle, the lines will be going toward, or will be oriented toward the particle. If we have two particles, then electric field lines, well, are bent in this particular way. Now, this is actually a drawing for an object which is referred to as a dipole. A dipole is an assembly of two oppositely charged particles. And electric field produced by a dipole has, well, if we draw the electric field lines, this would be the picture. If we take two identically charged particles, then the lines are going to be, well, here is a plane which is not crossed by the lines. They all bend either to one side or to the other side, and the one which goes straight actually ends here at that plane. Well, I want to show you just one more field, which is quite important technologically. It is referred to as uniform field. You will even investigate this field in the first experiment in the lab. You will have to draw the lines and something which is referred to as equipotential surfaces. So this is the answer. This is the answer to one of your experiments. Make sure that you recreate that picture. Yeah, I'm saying I'm going to add that. All right. So the direction of a line always coincides with the direction of the electric field vector. So for example, in this picture, if I take a look at the point this, I recognize that the electric field vector is going to be down. Over here, it is also going to be down. Over here, it is going to be down. Now let's take a look over here. So what will be the direction of an electric field vector at this point? Shout. Louder. Left. Correct. Electric field vector over here would be to the left. Consult with the neighbor what will be the direction of electric field vector at that location. On the other side. All right. Who votes that it will be to the left? Who thinks that it will be to the right? Good. Those of you who thought that it is to the left, you were right. Yeah, because the arrow over here indicates that the line is to the left. Can you find points where electric field is to the right? Yeah, where? Yeah, between, over here, for example. How about there? Yes, over here electric field is to the right as well. How about here? It's simultaneously to the left and to the right. How is it possible? What vector has such a property that it is in two directions, oriented in two directions simultaneously? Yes? Zero vector, correct. So electric field vector at this location has indeed value 0. All right. Now there are some more information. Yeah. If the number of lines per unit area is proportional to the magnitude of the electric field vector, which is also referred as the strength of the field. So the closer the lines together, the stronger is the electric field. All right. So how about if we look at the electric field produced by a particle, and let's compare the strength of electric field. How about at this point and this point? Is it stronger at a closer point or a further point? Which one? Closer. At a closer location, electric field is stronger. And why? Because the lines are closer. And now, how about that unit area? I have to imagine here a surface and compare how many lines cross that surface. The number of lines crossing the surface is proportional to the strength. All right, how about if we go to this field and let's compare electric field strength at this location with this location. Is it stronger on the left-hand side or on the right-hand side? They are equal. Why? Because the lines are equally spaced, correct. This type of a field is referred to as a uniform field. It has, at each point of the field, it is oriented in the same direction, and at each point of the field, the strength is the same. All right, I have already said that electric field lines are used to visualize the fields. Now, actually, I pointed here because when you read the book doesn't use phrase electric field vector. It refers to electric field vector as just electric field. The phrase in the book actually has a double meaning. So you have to recognize both meanings of the phrase electric field. Because field in general, or force field in general, is a region in which a certain type of force is exerted. Like, for example, if we say that Starship Enterprise escaped from the gravitational field of Milky Way. What does it mean? Consult with each other. What does it mean? Okay, can you say it? Can you say it louder?
What I'm saying was outside the range of exertion of the field, or negligible in the sense that it's
right. In other words, we are referring to space, right? It left space in which gravitational interaction with Milky Way existed. So the region is referred to as field. Now, look what electric field vector is. Electric field vector is a physical quantity which describes property of that field. At each location of that region, you have to imagine an arrow. That arrow is the electric field vector. Now, the book, and actually, I admit that most common electric field vector is almost my idea to avoid confusion. But physical quantity electric field characterizes the region of space. So electric field could be an arrow, or it could be a region where the interaction exists. Is it clear? All right. So this will be all for today. See you tomorrow.